I mean, they're gonna get more benefit as you grow up. Well, I get where she's really at practice. Oh, well, it's attendance. Yeah, like I'm gonna get. You know, it's night. That's bad. They're all. Yeah, but wait. Okay, so I was running a little bit the way for when you first from and then it just after like a update. Get me back on console.
Yeah. Oh, you're maybe.
Why, bro? Why are y'all crashing out on this? Why are you crashing out? Okay, today we're going to learn about a much more efficient way of finding a derivative. So we're learning power rule today, and tomorrow we're going to learn about derivatives for exponential and log, and then Wednesday, Thursday, Thursday derivative trig, and then Wednesday we're going to for more complex functions that are in where two expressions are multiplied together or divided by one another. How do we find the derivative or the slope formula for those? And then we're going to do a quiz review Friday and Monday, and quiz will be next Wednesday. Now, I'm going to use Tuesday to start the next section. Do not lose a day of instruction, but then also to kind of give you an extra day to review. So quiz will be next Wednesday, just over 2.1 to 2.5. Okay. So even though the limit definition is good in the sense that it allows us to see that connection between limits and slope and calculus derivatives, it is tedious and it's not very efficient in terms of getting to what we want to use to solve, to be able to do more with it. So we're going to learn about derivative rules called power rule that will allow us to find the derivative a lot faster, a lot more efficiently, but we do lose that. It does become more abstract, and we do lose that connection with slope formula. But now that we see that connection, we can go to the more abstract rule. So the first is the constant rule. The constant rule says that if my function is just a constant, then my derivative is always going to be 0. For instance, f of x equals 5. That's just a horizontal line. And what is the slope of every point on this line? 0. So because my slope is 0, and I know derivative is the same thing as slope, my derivative is also going to be 0 for any constant that I see. So imagine any constant is just a horizontal line, and that horizontal line is never going to have a steepness other than 0. So that's why my derivative is always going to be 0 for constants. Now, if I have a polynomial, or if I have a variable raised to an nth, it can be an integer, it can be a fractional value. My derivative is simply going to be just taking that exponent down in front, bringing it down as a coefficient, and then subtracting 1 from the exponent. So we bring the exponent down as coefficient from the variable, and then we subtract 1 from the original exponent value. Let me just do a quick example here. Let's say my function is 5x squared. my derivative, rather than going through limit definition, it's a lot faster now. We bring that exponent down. So that n is a 2. We bring that 2 down. What happens with that 2? Multiplies with what? 5, which makes it what? 10x. And then we subtract 1 from the exponent. That 2 becomes a 1. I can put a 1 there or leave it out. But now f prime is a lot more efficient now. F prime equals 10x. This is now the slope pattern for this original parabola graph 5x squared. So any point on this curve, I can use this to describe how the steepness of the graph is changing or existing on the original graph 5x squared. Now, this is going to be the derivative rule that you use more often than any others over the course of this year, as well as next semester. So there's going to be a series of derivative rules that we're all going to learn, but this is the one that's the foundational one. You're going to guarantee to see it on the AP exam. You'll use this more than any other ones. So despite the fact that it is the most commonly used ones, it does come with quite a few restrictions. So we want to make sure that we don't use it incorrectly, because it is easy to misuse it and end up with the incorrect derivative. So a couple of conditions that can really help is if you see radicals and you want to do power rule involving radicals, convert to rational exponents first, because if I can rewrite that square root of x to the fifth as x to the 5/2, then it's a lot easier to see what that n value is in terms of the rational value. And also, it's easier to know what to subtract 1 from. Okay. So for instance, let's say I had the cube root of x to the 5th. I would want to rewrite this as what? X to the 5/3. If I had the 5th root of x, I would want to rewrite it as what? X to the 1/5. Now this one gives students a lot of trouble. Square root of x to the 5th. This is x to the 5/2, but I see students do this where they think of this as x to the 1/5. Maybe that's because we don't see anything here, so we assume that's a 1, but that's not a 1. This is a 2 here. So this is not correct for this. Or if students realize that there's a 2 there that they want to read from left to right, so they write it as x to the 2/5. So I know this is just basic algebra, but I just want to point out that this does give students trouble. Anything with a square root of x to the power that's other than 1. Like I think everyone knows square root of x is x to the 1/2, so no one makes a mistake here. But students makes mistakes here. They write 5/2, they write 1/5 or 2/5, or any variety of things. So just be aware. On quizzes, I do see students misinterpret what that means. So that's the first thing that we want to do. We want to rewrite radicals as rational exponents. The second is variables need to be in the numerator before we apply the power rule. So if I had 1 over x to the 7th, I need to bring that x up before I do power rule. So that 1 over x to the 7th is the same thing as x to what power? -7. And then my f prime, I can then have a much more clear way of doing knowing what to do with that -7. We bring that -7 down, and we subtract 1 from the exponent, so -7x to the -8. This is my derivative for this function. Okay. We can't do this. We can't just look at that x to the 7th and say, well, my derivative is just going to be 7x to the 6th. Power rule doesn't work if a variable is in the denominator. It doesn't quite fit this condition. The condition for the function, the variable has to be up top if I want to go through this process of bringing 1 down and subtracting 1. The third condition is resolve all parentheses and fractional terms before you apply power rule. So if I had x times x squared plus 1 squared, I have to resolve all the parentheses and exponents before I do power rule. I can't do power rule for x and power rule for 2x and then merge it together. Now, having said that, we do have certain rules that can handle the multiplication of different functions, but we got to go through a separate rule for that. If we want to just do power rule, every term has to be separated with no parentheses getting in the way when we apply power rule. Okay, so we'll look at some examples of that, but and we're going to practice making sure that each of our conditions are met before we do power rule. All right, so example A, or 1A, y equals x to the 7th do we have anything that we have to do with cleanup? This is ready to go. Yes. All right, there's nothing that, there's no radicals to convert, there's no variable to bring up to the numerator, there's no parentheses to resolve. And there's a bunch of notations. F can become F prime, Y can also become Y prime. There's a lot of different notations to indicate that I want to find the derivative. So you can say Y prime. What's the derivative for x to the 7th? Yeah, we bring the exponent down in front, the 7 comes down, and then we subtract 1 from the exponent. So 7x to the 6th. You can also say y prime of x is equal to 7x to the 6th. It just means that I'm finding the derivative of my y with respect to my independent variable x. So there's a series of notations that are all acceptable. G of x equals cube root of x. I want to find the derivative using power rule, but I first have to rewrite it. How can I rewrite this? X to the 1/3. And now I can do power rule. G prime equals 1/3 x to the, yep. So then I got to subtract 1 from the exponent. So just be careful that when you're subtracting 1 involving a fraction, that you do need to match common denominator. Either you do it in your head or you write it out just to convince yourself. So this is my derivative, my slope formula for whatever this original graph looks like. Now, I'm going to ask you, when you find your derivative, that you resolve any negative exponents. So if you have any negative exponents, just bring it back down to the denominator. So this x to negative 2/3, I want to make it positive exponent. So I'm going to push that x down to share the same space as the 3 in the denominator. And when I do that, I can convert that exponent to positive. It's okay to leave your derivative in rational form, but if you want to put it in radical form, I won't take off any points, just it's up to you. And then again, you don't have to rationalize your denominator if you want to rewrite it as a radical. Okay, y equals 4 over x to the 5th. I want to do power rule, but what's out of place? I need to place that x where? Numerator, so I need to rewrite it as 4 x to the negative 5. So this should be my starting point for power rule, not this. Now let's find y prime. What's my coefficient? 20. And then my new exponent is -6. Make sure that we're subtracting 1 from -5. I think sometimes we get lost with negatives and we just do 5 minus 1, we make it 4. So just make sure that when you have a negative, that your number is going to get even more negative. All right, so my derivative is, I want to do some cleanup, push that x down to the denominator, so -20 over x to the 6th. This is my slope formula for whatever this graph looks like. All right, part D. If you have an expression with multiple terms, but all those multiple terms are nicely separated by either a plus or minus with no parentheses getting in the way, we can just really treat this like 4 individual power rule problems and then just merge it together once we find the derivative for each. But my suggestion is if you have a different separate terms and each term is at a different stage of readiness, then I would rewrite every term until every term is ready and at the starting line together, and then do the derivative all at once. I think sometimes the danger of finding the derivative of one and cleaning up the other is that if you go back and you try to check your work, it's really hard to check your work because you don't know, wait, did I do the derivative here or am I cleaning up? So even though it feels like you're doing additional work by rewriting your problem, I think it really benefits you 30 minutes after you're going back and you're rechecking your work, having clear steps is beneficial for you in terms of, if you want to catch a mistake, it's easier to catch if everything is nicely organized. So not every term is ready, but I'm going to rewrite the expression that is ready. So is 8x to the 2/3 ready for power rule? Yes, okay, so I don't want to do the derivative yet because not every term is ready. So I'm going to write this as 8x to the 2/3 minus the 5th root of x. Is this ready? No, so I can rewrite it as what? X to the 1/5. Okay. There's 2/3 root x ready for power rule. There's two things that needs to happen. What needs to happen? Yeah, I need to rewrite that root x as x to the 1/2, and that x is going to come up as x to the negative 1/2. Now, anytime you want to move a variable, make sure that you don't feel like don't move the coefficient in front of it. That 3 is going to stay below, and it's only the x that needs to move. Sometimes we feel like, oh, these are next to each other and they're connected, so I got to move everything together. These are next to each other, but they're not connected in a way that they can't be easily separated. So you move the x, but the 3 is not the issue. So I'm going to rewrite this as 2/3 x to the negative 1/2. And this is my preference, is even though this x is technically the same level as the 2, I like to have that x to negative 1/2 as its own thing, and then the 2/3 as its own thing. That way the 2/3 feels like a coefficient, and you don't have to stare at a number below the variable. I just want to show you what I mean by that. Like this, these are the same things, but I think for power rule, this just feels a little cleaner because it doesn't feel like, oh, what do I do with S3 below my variable? It feels like that 2/3 is clearly outside the space of my variable. And this feels like a coefficient rather than a denominator. So it's not wrong if you do it this way. I just think visually it's just a little cleaner if you just have any fraction in front rather than below your variable. And then the 0.875 is just a constant. It's ready for my derivative, but I don't want to do any derivative just yet. So now every term is ready. So now I can jump into my power rule step. What comes down? 2/3. Okay, I'm just going to just skip a step here. What's 2/3 times 8? 16/3. I'm just going to multiply that with that coefficient. What's my new exponent? Negative 1/3. Okay. Minus 1/5 comes down. We're just doing power rule for each of these, treating them as a separate problem. What's my new exponent? Okay, bring down the exponent. What's 2/3 times negative 1/2? What's my new exponent? And what's this? Constant, right? That's just a horizontal line that is between 0 and 1. And we know any constant is just going to be a straight line. And any horizontal line is always going to be a 0. You don't have to put a 0 here. I'm just showing you what's happening to that. And now I'm going to clean up my derivative. So any negative exponents, I'm going to push it down to the denominator. So this looks more complicated, but it's doing the same thing as other derivatives. It is just describing the slope behavior of what your original graph looks like. Okay, next page. Now we know that a derivative can get to a slope formula, but then we can go one step further and actually find the steepness at that point on the curve. So let's do that. We're going to get this function ready for derivative power rule. We'll find the derivative using power rule, and then we're actually going to find the steepness of that curve at this particular point. Okay. Yeah, I'll have you try it. See, can you rewrite the function, get it ready for power rule, apply power rule, find the derivative function, and then end with the slope at x equals 2. So here's our function rewritten in a form that is conducive for power rule. And now we can apply power rule, do some cleanup. And now I can evaluate the steepness at a particular point. So this tells me that at 2, this graph is going to have a steepness of -1/4. It's going to be a very gradual but a negative slope. You don't have to draw the graph, but just to kind of show you what this graph looks like. 1 over x squared is going to look like this, and it makes sense that at 2, you're going to be experiencing a negative slope, but it's going to be a very gradual negative slope. So that's what that f prime of 2 is telling us about this original f of x graph.
Won't you get the equation with a tangent?
Okay, yeah, so let's talk about example 3. Okay, so it says fx equals cube root of x squared. Write the equation of the tangent line at x equals 1. So to find a tangent line, we're going to go through, create a point slope at this point. So point slope, we first have to find the point. So I'm going to have you guys try this. Let me just talk about the big picture here. How would you normally find order pair? Plug it to the original, right? So your order pair is going to come from the original function. And then your slope is going to come from the derivative, right? So f of 1 is how you find your order pair. F prime of 1 is how you find your slope. So you're going to go through the steps like you did with example 2. You're going to get this ready for power rule, apply power rule, plug in 1, get the slope. And then once you have your order pair and your slope, you're going to put it into point slope form. And then this line is going to skim the surface of this curve and therefore creating that tangent. All right, so try those steps. Find your order pair, find your derivative, find your slope through your derivative, and then you can put it into point slope form. All right, I'll follow up the steps once you guys Okay, so my function is x to the 2/3. If I want to find f of 1, I can just plug 1 into, and for x, the cube root of 1 squared is still 1. So my order pair is 1, 1. My derivative, bring down the 2/3, subtract 1 from the exponent, 2 over 3x to the 1/3. This is my slope formula. I can plug 1 into my derivative to get my steepness at that particular point on the curve. My slope is showing 2/3. My order pair is 1, 1. Point slope form, replace x1, y1 with my order pair, replace slope with 2/3. And you can leave your equation in point slope form. If you want to get it into slope intercept form, you won't have points taken off, but you're just taking an additional step that you don't have to. So my suggestion is leave it in point slope form. It's the most efficient version that will get you full credit. Any questions? Okay, does anybody still need to look at example 3?
If we're trying to find some tensor line equation, while doing the steps, we have to take the derivative of whatever, can we leave it in whatever form you want to, just to like move on with the problem?
You're talking about whether this form is acceptable?
No, I'm talking about when you find f prime of x, can you just leave it in that 2/3 x to the -1/3 form, so you can just move on with the problem? Find what you need to find.
Oh, you mean finding f prime of 1? Okay, well, okay, let's say this. If I were only asking you for the derivative function as the if that's the solution of the problem, then I want you to represent your derivative with positive exponent.
Right.
But if that's not the final step, if it's just a kind of a stepping, like if it's only a middle part of the problem, then I'm not going to be so worried about whether you clean that up or not.
Okay.
Yeah. Are we good with 3? Here's number 4. All right, now 4 looks complicated because you have that numerator and denominator, but we have to be careful that we can't just do power rule for each of these terms and then just treat them all as independent. These are connected in ways that requires us to do cleanup before we can do power rule. These are not independent of each other. These are connected, but we can't quite see what each of the variables' exponents are because they're all kind of connected through this division. Now we are going to have something called quotient rule that can handle a derivative between numerator and denominator, but we can actually do power rule with this one because there's only one term in the denominator. That's the key here. If there's only one term in the denominator, we can actually split up into individual fractions that otherwise would cause an issue. If the denominator had multiple terms, like if it was like 2 root x plus 1, then we're stuck with having to go through a more complicated process, which we're going to learn later. But there's only one term in the denominator. We can algebraically, it is possible to split up into 3 individual problems. In this case, we can think of as 3 separate individual fractions. Clean up each fraction, get each ready for power rule, and then apply power rule separately. So let me show, I want to talk about how we can do that. I'm going to do kind of multiple cleanup steps as I separate into individual fractions. So this is the same thing as this over this minus this over this plus this over this. And as I do that, I'm going to try to clean up my radicals along the way just so that I don't have to, I can save steps in terms of having, not have to write the expressions too many times. So the first step, I'm just rewriting it as x to the 4th over 2x to the 1/2. and then minus 3x squared over 2x to the 1/2 plus 4x to the 1/3 over 2x to the 1/2. This way, we're beginning to see how the denominator is impacting each of the terms. And then we're also moving towards making each term independent and therefore able to apply our derivative. Now, each of these fractions, what do you notice is out of place? Let's start with the first term. What's out of place for the first term? If we want to do power rule. The x to the 1/2. Is the 2 an issue? No. So the 2 stays below. The x to the 1/2 is going to come up. Actually, I'm going to rewrite this so I can show each of the steps. Now, if I want to merge the two variables together, what am I going to do with the exponents to allow for that to happen? Subtract. Yep. So if I have a to the m over a to the n, as long as I share the same bases, I can think of it as a to the m minus n. And then along the way, I'm also going to push the coefficient out in front so that I don't have to stare at a number below my variable. So this is really a coefficient of what? In front of x. This is the 1/2. And then I'm subtracting exponents. So what's 4 minus 1/2? Yeah, so really 8 over 2 minus 1 over 2, because anytime I'm subtracting fractions, I got to match common denominator. So 4 is really 8/2. 8/2 minus 1/2 is 7/2. Now, you don't have to show all the step here. If you can do this in your head, that's fine. I just want to make sure that we're seeing how each of these numbers are coming from. I'm going to push out the 3/2 as a coefficient. And then what's 2 minus 1/2? Yeah, 4 over 2 minus 1 over 2 is 3/2. 4 over 2 is coefficient. I'm just going to make that a 2. And then 1/3 minus 1/2, I need a separate denominator here. I really need a 6, right? So it's really 2/6 minus 3/6, which is what? Negative 1/6. Now, we did quite a bit of work here. I think I've seen students in the past where they feel like they've done so much work and they'll leave this as their derivative, but we haven't done anything calculus yet. All we're doing is we've cleaned up every term to get it to the starting line so that we can apply a power rule. So we still have to do power rule. All we've done is we've got the conditions ready so that we can apply power rule. Okay, so now f prime. Bring the exponent down, multiply with the coefficient, and then subtract 1 from the exponent. Bring the 3/2 down, subtract 1 from the exponent. Okay, so now I'm just going to do there's not much to clean up, just that third term. I got to deal with that. This is the type of problem that is the most intense in terms of like, step intensive in terms of problems involving power rule. This is as messy as power rule can get when you have to deal with these individual fractions, and then you got to deal with, common denominator with the fractions, and yeah. Any questions? Example 5, find f prime if the function is 3x times x plus 1 squared. Let's go through each of the conditions if we want to do a power rule. Do we have any radicals to convert? This is okay, right? Do we have any variables to move up to the top? Do we have parentheses to resolve? Yes. So we got to FOIL everything out, expand everything out, get all the parentheses to disappear. And then once every term is individually separated, then you can apply a power rule for each. Okay. So make sure you take the time to FOIL out. Don't just distribute that 2 through. Write the binomial twice. As a reminder, you got to expand. So I would expand the x plus 1 squared first, then distribute the 3x. Remember, 3x can't distribute through the x plus 1 yet because the order of operation tells us exponents come first. So take care of that x plus 1 squared, then distribute the 3x, and then get every term separated, and then apply power rule. Okay, try that. See if we can arrive at the same place. Expand out that x plus 1 squared, distribute the 3x through. Every term is now ready for power rule. So now we apply power rule, 9x squared plus 12x plus 3. The reason why the derivative of 3x is 3, 2 reasons. The derivative of 3x would bring that 3 down, sorry, 1 down. And then what's the new exponent? 0. Anything to the x0 is going to be dropped out. And also, if you look at this, does this actually need calculus to find the derivative? That's just y equals mx plus b, right? This is a linear graph. Any linear graph, the coefficient is the slope. So, I mean, we can go through power rule, but we can also use our algebraic knowledge to know that the derivative of 3x is 3. All right, so let's spend about 10 minutes starting our homework. So you're going to go to page 15. Make sure you do this on a separate sheet. See your individual work. And then the pages, the assignment problems are on your calendar. If you need scratch sheet, I have scratch sheets at all the top of all the shelves.
You know by when we expect to have our EB test?
I have them half graded, so Wednesday, hopefully. Wednesday, hopefully.
No, I think grade's good.
Pretty good. A's and B's, mostly A's and B's so far.
I'm gonna break the curve, be honest. Like breaking curve means getting 100. I'm gonna get a 0. So breaking curve. Oh, it's not easy. No, my gosh, for the average was like at 50. Yeah, that was insane. That was the one test I did like above average on, and it was still like a 6.
Yeah.
How would you do like
47. Your actual.
These are all nice diagonal lines. So any derivative is just the slope. So just find the slope at the point on that line, and that's your derivative.
Okay. It says u of x is f of x plus g of x. I'm supposed to find the slope of both and add them.
That's right. Find the slopes of both individually and then add them together.
Okay. Perfect. Okay. Fine. Okay. Fine. Because you know. I'm real bored actually. It's even now. There's a guy, how you think, why?
There's something. Yeah, okay. You need to advertise your. Oh, I do. Yeah, yeah.
We got the numbers of.
I'm not doing like listening. I don't. I'm not doing the baseball part. I can't say I'm not listening. I think that's because you played. Yeah, actually.
Bro, I'm not.
Have you got who you voted?
Bro.
Okay, so it's probably like.
If you guys try each problem, you guys can check your answers with what I have on the board.
What's the one?
Oh, no, it's happening.
I have a question last week, or did I think things. As number one, you got. Or finding the derivative. Got here, and then you got to. 2x.
Doesn't the first one?
How did you get this?
Going through power rule or going through the definition? Yes, because with the power rule, a is just some coefficient like 3x. 3x becomes 3, so ax also becomes just a. This x squared is just 2x. And then minus 1x just minus a.
Oh, I see.
Imagine this like 4x. 4x would just become the coefficient prime, which is 4. With ax, so the coefficient of x is a.
What's your third?
It's good for that. Bro, wait that Jimmy's mine. It's so cute.
Well, I just mean for God. So
If you get big, that's crazy. So you're copying. Okay, great. You're copying. So you're copying. You're engaged. That's just a technical approach. I thought you were like down there just like repeating.
Okay, let's keep working for another 5 minutes. Thank you.
Just teachers big. Wait, what's the difference? Well, get there. With that, say it. Okay. Why? I'm gonna be quiet, little boys. Shoppers. Little mind. What? Bro, I was
What is that?
Bro, I would know. I would
The first one, okay, I got the
I
answer,
would
but not
read
the
the first snake eating. What is that?
on the
I
homework.
was every little drop of first snake eating.
How did you do it? Did you do it?
Little first snake eating.
Oh,
Very motley fool.
so I think I just gas it, just so thanks for getting me right now.
What being said?
I don't know what I did to do this. I just like.
Go quit. Yeah,
Yeah, so I guess it just,
It's just by looking at the budget, this is really.
I don't know why that's square root of it. I guess if it is just look, then yeah, it's kind of just right there in front of you.
Oh, I hate that. I hate.
You remember?
Yeah, and you keep on popping up and you gotta use it for the AP test.
But do you need to know, like, so I'm looking at that based on rhetorical device. Do you only need to know the definition or do you need to like know how to apply it?
I think the definition and how to apply it, but that is not that you're hardly to the plan. You just need to know how. And you need to know the definition and all that.
It's just like a.
It's just like a. It's the first two.
It took way more time than one.
I never really studied that, so I got.
Well, at least you got the college back.
Yeah.
Very on that clearance out of 100. I should expect. Hey, that's the.
What does it mean when it asks for the equation of the normal? The normal is perpendicular. So just take your slope and make it opposite reciprocal.
I don't know what we're doing.
Wait.
I could put like 18 times the bottom.
It's like, oh wait, I have something for you.
That's a reading.
So guys, one last thing, some students have asked about, what that normal line means. So normal line means perpendicular. So opposite reciprocal of the parallel line.
So it's just if like worst case.
Yes.
I didn't. I actually don't have the velocity time graph. Like where it's just a straight line.
Bro, I didn't do it. I'll take the side of this. For the next year. One charge. Yeah, but building. That's first. Thank you.
Absolutely.
Well, I never even wanted.
He's always like by dad.
Probably.
Right, Go ahead and finish your homework for tonight. Come up with, there you come up with your problems.
Those are right.
Okay, but I get my work done.
I mean, if you could have worked on credit.
You know, there's don't.
Wouldn't make. Why was it?